we try a little bit in this tutorial to bring different technologies together and show how we use Python to combine standards from the geospatial community and get our data from ECMWF. There's a bit at the beginning, a bit of explanation to do. So we'll start off a bit talk, but then we have 3 sessions to go into more practical work. And as I mentioned, there's 2 links you might want to have a quick look at now. The first one is a hosted service of the Jupyter Notebooks. If you go there, you will be able to follow straight away the course. Or you can go, the second link is on GitHub, where you can find the Jupyter Notebooks, clone them or download it as a zip file, and then follow it through that. But then you have things to be installed yourself. That's on your machine.
What things?
The dependencies like OSLib, matplotlib.
So all the libraries. So basically, on the Jupyter Hub, all the libraries we need for the tutorial are already installed. So it's a safer environment where you can run everything
yes,
through.
if you can try the first link.
It requires that I give an authorization to my...
So GitHub, yeah. So you have to log in with your GitHub credentials.
Is that why? Okay.
Yeah. Yeah.
Thank you.
Otherwise, you can just clone it from GitHub, but then you need all the libraries, basically.
Yes, and libraries, matplotlib, I guess most of you will have. There's netcdf4, OSLib, and unfortunately at the moment you need an OSLib with a fix, so there's a link to another Git repository you need to follow, unfortunately. That's why we set up the other environment. Please also, I mean, this is the first time we're trying this kind of tutorial, so if you have any question, please raise your hand and we look into it.
And if you want to exchange like any information and stuff like that, we have a Slack channel specifically for this talk. It's fry_Wagemann. So if you're on the Slack team, just look for that channel and join it, and you can exchange links and stuff.
Does anyone else encounter a 500 internal server error? Okay.
Oh, with the first link?
Yeah, with the first link.
Oh.
Oh.
Okay.
Yeah, mine's not moving. It's not loading. Maybe someone else?
Has somebody managed to do it? You got it fine, okay. Can you perhaps retry to see if it's just perhaps...
Waiting.
We're all doing it at the same time.
Yeah, I just wondered perhaps it's yeah. Did it? Did it?
Time out.
Time out again.
Never try again.
Yeah.
Is that your birthday?
That was my first. I've loaded it, but I haven't run a cell or anything, so I'm not.
Okay, but it's you were able to load it. So, quick hand sign. Who has problems at the moment? If you could perhaps try again, and otherwise if you could switch to the GitHub.
Is there anything non-standard except for OWSLib?
To be honest, the standard OSLib will actually work for some part of it.
Yeah, for some part, yes. For
So
the WCS part, but there is then in the notebook a link which library you actually need.
Okay.
But so most of it will actually work.
Okay.
Yes.
Because that's easy to install.
Yeah.
Okay, good. Do you think you need a bit more time to... It's still time out? Sorry, I think then perhaps the GitHub.
The GitHub one?
Yeah, I think that might be the better.
And it's compatible. What you're showing is compatible with 3.6.
To be honest, we do everything to 2.7. I mean, we try things out with 2.7. I know.
You warned us beforehand.
What I perhaps do is, and I start with the general presentation a little bit, and then we check after that how everybody has gone on with the links. Unfortunately, it means I cannot keep the links up, so if everybody can take them now. Okay, quick hand sign. Who has heard of ECMWF before? Wow, more than I thought. The European Centre for Medium Range Weather Forecast is an intergovernmental international organization which is located in Reading here in the UK, west of London. And we are quite a small organization, about 300 people. Even so we are called European, we are actually not directly linked with the European Union. So, and you can see from our member states that we're not exactly the same member states as the European Union. We have different member states, and some of the European Union are not member state of us. So it's intergovernmental independent. What we do is we're doing weather forecasting, numerical weather forecasting, and what our mission is to support national weather services and the general weather industry with medium range weather forecasts, which means anything from 3 days and beyond. So it's normally 3 to 15 days. It's what's called medium range forecast. And it makes sense to actually work internationally together, because wherever you want in the world to make a 3-day forecast or anything longer term, you need a global forecast. You can, 1 or 2 days, you can get away with looking at a local situation, but anything beyond 2 days, you will have to need look a global model. So instead of all these countries running their own global model, they came together in the 70s and decided, let's have one supercomputer center which does it all for us, and then we can use it from them. And it's more efficient to do it all together. So we are a 24/7 operational center. Twice a day we are issuing our forecast, which go all to the weather services, not only in Europe but around the world. It's a very time-critical job. It's a lot of data. We're generating, it's terabytes for each forecast, and we have also an archive which now reaches over 180 petabytes of data. So it's very time critical and very large data sets we have. To cope with all that and to push forward, because you can imagine forecasting up to 15 days is quite a challenge. We have also very strong research focus, which is not all done at the center. We're bringing together different research activities around Europe and coordinate them, and also work with them and cooperate. Member states I mentioned. Beside of our core activity, we are also operating on behalf of the European Union two services for them. You might have heard about Copernicus. Copernicus is an initiative of the European Union. The European Union has been for decades a big driver and supporter and sponsor of research work on Earth observation and environmental services. But they were mostly short-term. So some years back they came together and said, let's have a long-term program which goes beyond 2-3 years projects. And that's the Copernicus program. There's different services, 2 of them, the climate change service and the atmospheric monitoring service. They are hosted or operated by ECMWF. And as you can imagine, climate change services, the aim is to support businesses and industry to prepare for changing climate and prepare for that and make decisions on future projects. Atmospheric monitoring service is more direct link to our usual business, is about forecasting the quality, air quality, pollution, and assist also governments and businesses to react to these challenges. Yes, I think that's so ECMWF. A quick word about our data. We have open data, but our core forecast data is not freely available. As I said, we're supporting national weather services, so they take the data, they're including it, and then they will issue forecast out of this one. So they use this forecast and then give it further. Then we have a lot of public data sets. Everything actually sponsored by the European Union is actually open and accessible. They're very keen on this one because they really want to encourage that businesses and agencies picking these services up. And that's why also we are interested with projects like the one we are working here to find ways how can the community, businesses get our data and how they can build services and new applications for the community, for businesses. But there we have different services. Related to climate change, you will have something called reanalysis. Reanalysis is going back. When people talk about climate change, they always think about the future. but important part is also to go back in the past and reanalyze which was the weather in the past, so that you can see patterns and how the climate has evolved, and to make some prediction for the future. So that is what these, when you see reanalysis mentioned here, that's what this is. Then we bring in different forecasts together around the world. Forecasters normally don't look at just one forecasting model. They look around the world at different centers, what they're forecasting. And we have some research data sets where we bring these data sets together. So they're not real time, but they allow researchers and businesses to learn from it. And it's very interesting in the age of machine learning to look back at past data to learn from for future decisions and building new application, how you want to use weather data. I mentioned already the atmospheric monitoring service. So just to say that not all our data is free. You will see the access, we have to access our web services, that you will have to provide a token, and the token we use here is public. There's other tokens, but they're IP address limited, so you cannot access it. But the public one, you should be able to access at least the Copernicus services and some of our data, which is free. So our data itself, we're doing numerical weather forecasts, which has the advantage that the data is actually quite structured and quite predictable, because it's a numerical model. So we don't have much on the sense of missing data or outliers very much. So it's output from numerical weather forecast. But what is more challenging is the various dimensions we have. So weather forecast is not only geospatial in lat and long, it also goes in time. And then we're also going into height. And in height, in weather forecasting, you not go in geometrical height, you not go 5,000 meters high, you go in pressure levels. So we talk about 500 hectopascal as a height. And this is simply how weather is moving. It's along pressure levels. It's not, the weather does not care what is a geographical height. It cares about where the pressure is of the atmosphere. So it makes sense for meteorology, but also users like in aviation, they're also used to working with pressure levels. So you will see that coming up in the thing. Then we have something different, which brings us to 5 dimension, and that is we're not just running one forecast, we're running actually 51 forecasts. And the idea is that you actually run a set of forecasts called an ensemble, and you actually you have one which you start with the best starting condition you have at the time of the atmosphere, and then you start 50 with slightly changed condition. And then you can see from how these 51 forecasts behave statistically, you can have an indication of the certainty of your forecast. So if 20 forecasts agree, then you can see that there is probability into a forecast of all 50 agree, you can be very certain. If you have not more than 3-4 agreeing on a weather pattern, then it's a high uncertainty about if this will happen. So it helps forecasters to predict the certainty of a forecast. But this is, of course, very time-consuming and data-consuming. So it's quite a challenge for users of our data to download all this data, make statistics. So that we have some products like mean and spread values, which are already calculated over all these ensembles. So coming to the end of the presentation part, what we now want to do is we're going to go a general geospatial data workflow. So the first thing is, of course, getting the data. As I said, normally when you might have data project, you might have a lot of to do with clean up the data things. Because it comes out of a numerical model, which is a very ideal situation, you actually don't have to do so much cleanup work. The data is actually quite clean and can be straight used. But still, you want to do some data processing for your analysis, but you also want perhaps to subset data. You want to have time series, so that we will explain a little bit how you can do that. And then you want at the end, of course, a nice little picture, so or something you can present. So visualization is always quite important. So it goes from the access processing to the visualization. And I mean, over this process, you will reduce the value, the volume of the data, but hopefully what you get is you get more information out of it, because in the end, even if you have much less data at the end, only a small PNG possibly, it should really have something much more information for the users than all the data you have. So we have at the end some more links if you're interested to find out about ECMWF, about our data service catalog if you're interested to browse a little bit more. We definitely don't have time here. And then also about, for example, the climate data service and Earth Server 2. Earth Server 2, perhaps I should mention, that is actually the project where Julia and I are here for. It's a project we have with the European Union sponsored. It's a 3-year project to explore how we can use standard geospatial web services to bring our data out. We have already existing services to pushing out huge amounts of data, but they're very specific. They have been proven over the last 30 years, but they're very specific to our community, and they're very hard to use for for users outside our community. So we are looking at standards like the OGC standards, which are well established, to work with them so that if you interface to our data, you have the same effort as you have with other services, and you not have to do anything special for ECMWF. This is this Earth Server 2 project, and we're having a test service, which Julia will talk later about, which we use for that. Before my voice goes, yeah, I'm going over now to the first tutorial. I don't know how we are for time. No. Okay, I mentioned already these OGC web services. Quick hand sign. Who knows about OGC web services? Oh, wow, less than ECMWF. That I have to write down. Because we're using them because we're told everybody uses them. So that's no. It's starting in the 90s. Perhaps I give a bit of background information. Starting in the 90s, it became very clear that there's more and more services where there's geospatial data. Geospatial data means any data set you have which has any coordinate involved on Earth. So the idea came up, let's build standards for the web, how I can retrieve these kind of information. OGC is an Open Geospatial Consortium. It's an organization which is located in the US, but is quite international now, is quite popular also in Europe. So a lot of, especially government organizations, are involved with the OGC. The European Union has this INSPIRE program. INSPIRE program is where they're trying to encourage more and more government data to be available freely and easily accessible. And they have also decided to go mostly with the OGC standard. So that means they're quite popular. And I think you will find there's a lot of OGC-based standards around where you can get public data sets in different countries. If you want to find them out, Google for INSPIRE and your country, and you should get a portal which gives you the different data access. For us, of course, working with the European Union, is also very interesting to use these standards because they really want us to use it. OGC is a family of standards, and because when you have geospatial data, you can have vector data, which we normally don't have because if you have border data of borders, coastlines, this is not really our business, but you might have as a street road maps or something. So you have this kind of vector information. They have something called a web feature service, which we'll not talk about today. And then on the other hand, they have raster data, and that's exactly the data we have coming out of our numerical model. This is data which covers a wider area. So that is not only meteorological fields, it's satellite imagery. That's actually the main driver and the most popular in these services. And then also digital elevation models. This WMS is actually quite long around. It's used a lot in the back where you get maps. When you introduce it, often it's used for like Google Earth or something to integrate a new map layer or something. So it's a standard which is quite widely used, but possibly not always visible to users. But it allows users to get data. And there's the different standards which Julia will cover a bit. The web coverage service, web coverage processing service. These are the two we will talk about. And then it's the coverage transitional one we're not talking today about. In between is another what I already mentioned, the web map service where you get maps and images. This is what is mostly used, as I said. But we are mostly interested in the maps, which I will quickly go an example. But then the main example and what we're interested with Earth Server is the data, because the data will allow you as a user possibly to build your application. Images are nice, but you have to get what is provided. You have less flexibility with that. The data will allow you to build services, especially if you get a time series, you can build an application with that, showing a time series for your location. Okay, just to quickly show how it looks. WMS, this is now the web map service to start with. What most standards have is they have one web URL called get capabilities, and that is actually an XML document, and sometimes quite big one, which describes what the service is offering. In case of a web map service, it's the layers, the graphical layers of maps you can request from the service. And then you have another request to get the map. Just to quickly show how that looks. If you want to, if you see the links on your thing, you can also click them. Perhaps I should have done it. Okay. If you can see, please don't look at it because they're massive big documents. But the good thing is they're machine readable, so you can write scripts. You can write on your web, on the web client side, you can write scripts, but also on a Python script side, you can access this information, and we'll show you in a second how from Python. So you get all the information you need to make use of the service, and then as an example, here's one example how you can get this map. Oh, it's already there, sorry. And this is, for example, now one layer I requested from our service. You can see that it's actually, that's transparent background, so if you overlay, you don't see where there's no data. But that's a map, and of course you want to somehow integrate it because you need to know what area that is. That is, you might guess it's worldwide, but it could have been a sub-area over Europe or something. So there's something you have to do on your client side to understand what this request is. And if you look at the request, it's a simple form. You're just saying, I want the layer composition of AUD and 550, and that's a challenge to know what this is. You want to quickly do the...
Yeah.
Give my voice a rest.
Okay, just a question. The people who wanted to access the Jupyter Hub, have they in the end be able to access it? Okay, sorry, there was a timeout, but the guy he told me, like, if you try it, and then you should be eventually be able to access Jupyter Hub. Okay. Good. So so Stefan already introduced you to a web mapping service, and the web coverage service has the same structure to actually access the data. So we also have a get capabilities document where we get the information about the service and also what data we can actually access from the service. So it basically looks the same. It's an XML document. But it tells you, in the end, there, like, what specific data we can access, like ERA discharge data or Chef fire weather index data, for example. And then we, in a web coverage service, because we have like an overview of what data is available, but if we want to have more specific information to one specific data set, like for example the bounding boxes or the temporal coverage, there's a request we can use to say, okay, describe me the coverage, and then the coverage ID I'm interested in is temperature to 2 meters, for example, 2 meter air temperature. And the request looks like this. So we change the request type to describe coverage, and then we say we're interested in the coverage ID temperature 2 meters. And if we open this, then we get also an XML document, but then with much more information about the geographical extent and also the temporal extent, and also the number of rows and number of like the number of pixels or valid data points for valid data points. So it gives us more information, and we can now better work with the data. So we know it's a global data set, and it's available from 1979 to 2016, basically. And so this is like just getting the metadata and some information. If we really want to get the data out of the service without required download, there is the request get coverage. And there we say, okay, get the coverage. We also specify the coverage ID, in this case also temperature, 2 meter air temperature. And within the request, we can also subset our data. So for example, if we're interested in just one time information, but the entire global information, we can say subset equals, and then we just do a subset on the time axis. So ANSI, and then in this example, we do 15th of December 2013. But the same we also could do for subsetting latitude or longitude, if we're just interested in Europe, for example, or Africa. And in this case, I specify format also as an XML, but we will see later that there's also other formats available, which is more useful or more handy to work also within a Python script. And so this is an XML, and in here we see actually the actual data values. Okay. So this is the request types for WCS. So get capabilities, describe coverage, and get coverage. And then because geospatial data are usually large in volume, so we have to process the data and actually to reduce the volume and to get the information we actually need. But we don't want to download the data, so best is actually to have the processing right at the server side. And so with these web services, and especially with the web coverage processing service, which is an extension of the web coverage service, we have an opportunity to actually process directly the data on the server and just get the information we actually need. And this looks like it's a similar SQL-like language. So basically we use then a request, it's called process coverages, and then we build up queries for our data. And so in this case, we say, okay, for every point in our coverage ID we're interested, so in temperature 2 meters, please give us back the entire global field, but we want only to have the subset on the 31st of December 2015. And at the same time, we want to convert the 2-meter air temperature data from Kelvin to degrees Celsius. So basically, we get back the converted field in the end. And then from this web coverage processing service, it takes a while. We get a CSV back, which we can then easily integrate or store into a NumPy array, which we will show later. Okay, so this is enough theory, I would say. We now get our hands dirty with some examples how to access the data with a web mapping service.
Yes, I guess you wonder why on PyData we are talking not about Python, so we now start actually to go Python-wise. As Julia said, we start off with WMS simply because it's most, how you can say, most used, most established of all these OGC services, and because it gives you a visual result, it's also the easiest one to show something, have something visually to show you. What we're using Python for, I mean, we're also relatively new to Python. We're only over the last year starting to use Python, and also now Jupyter Notebooks for training, we're also only really starting now. But what it brings nicely for us is that we can bring all these things together, these OGC standards, our data, and allow users now really to do something with our data easily, which can be very well trained through these Jupyter Notebooks, but also very exchanged, and then later in the scripts can be also run as an application. So, as we mentioned earlier, the key for assessing OGC standards is actually a library called OWSLib. For the WMS, you can use the standard OWS, which is on your system if you have it installed, and it's under pip. It's a very common package under Python, widely available, definitely under 2.7. Sorry, but I'm sure it's also on the 3. So if you get this, if you want to follow it, what we have done is we actually did very kindly prepare everything out for you, so you can step by step following through. I assume that everybody's okay with going through Jupyter Notebooks. Anybody want a quick go through? I mean, if you just want to go through step by step executing these the different steps, and what you do is if you highlight, like here I do now with the cell 1, and you get a green border. If you just type space return, and then you will execute this one. What you will see is you will see above the Python tool just this small circle. As long as it's dark, it actually means it's processing on the very top. Now it's white because it has stopped processing. The first step you did not, there was not much to see. But if the second one, where we now did the request to the WMS to get back an object, and that is now the WMS, as I mentioned, from ECMWF, and we use the token public, so you get all the public WMS services returned, and you can list the contents of it by going in your second bar, say WMS.contents, and then hopefully you should all see a list of the content of what you can ask from the WMS. It's a nice long list, and you might say, oops, what is all this? Because if you're not familiar with some of the terms, I mean, you will guess what grid and rivers is, but all the others might be a bit more, not known. So what you can do is next thing you can ask the title of each of these layers if you want to see what they do. So if you go to this cell and execute it, you can then find that the composite CO2 surface is the carbon dioxide at surface. And that is a typical example of what this the Copernicus Atmospheric Monitoring Service does, one of these parameters they provide. So if you want perhaps quickly you might have another layer you wonder what they mean. If you want to take a name and want to try it out, so you replace it, you can use the same cell if you want, and then execute it and then see that you get the explanation from that. But this also means if you build an application and you want to build a title in your application of what product you have, you can use this information directly from it. And that should be hopefully a self-contained description. Of course, what is Erica? That's a different matter, but I think it's so there are some projects which you have to refer to possibly from the thing. Then you can get other information. For example, very important is to find out when you have a WMS, you need to find out what are you actually get which location. In the case of ECMWF, it's quite easy because, as you can see from this example, the bounding box in lat long is actually, it's the whole globe. And most of our products, I think with very few exceptions, they're all global. So it makes it relatively easy. If you work with other OGC web map services, you might find that you need to check this to see that you overlay it correctly in what area it actually covers. A lot of service in the US only covering, for example, the US. So you would have to, or a lot of national services just covering their own national areas. So it's worth checking what area you get. And as I said, for ECMWF, it's quite relatively easy. I said with the WMS, of course, when you get visualization of a parameter back, then it has to be styled somehow. We have different styles which we offer, and that's normally most web map services do. They have a range of styles to offer. It's not always easy to know what's behind these the names, but what you can do is you can ask for each layer. If you're interested in one layer, you can ask with saying .styles. You can see what styles they're offering. So then you can choose any of the styles provided there. So here you can see the different styles mentioned for the composition CO2 surface. Just to check, but I think that is also very common, is which services, which operations this service lets you do. The get capabilities we already have done in the back because we got all the information of the layers. Get map we already mentioned, that is the map. And then there's another feed, another operation called get feature info. And that is unfortunately something where the standard is very vague and just says, you can give to this function, you can give a location within the bounding box, and then it should give you information back about this location. Unfortunately, the standard says it's up to the operator to do, and that means that's where the standard goes out, and that's where it's hard as a programmer, application developer, to rely on what you're getting back. For ECMWF service, you get the value at this location, whatever layer you have. but in other places you get actually a little graph of a time series, for example. So it depends what you get back. So this is something, if you go for different web map services, you need to check very carefully what the service replies. Then you can check which kind of graphical products you get back. What normally most services do, and what the easiest to rely on, is the PNG, because you can put it everywhere. That's perhaps the easiest one. SVG, PDF, PostScript are, or the Google Earth one, they are more the fancy ones if you want to overlay something. But the PNG is normally something you can very easily, especially also when you have like this Jupyter Notebooks, is more easier to integrate than the others. So now we have played a little bit, get some information from the service. Now it's actually, we want now to plot something. So here's some example code how to get 3 different layers from our service and how to overlay them and plot them within the Jupyter Notebook. The first thing to have, to overlay anything graphical from what you do with Matplotlib, in Jupyter Notebooks you have to have this magic line of the percentage Matplotlib inline that ensures whatever you do, it goes inline. Then we're including Matplotlib image in PyPlot. We have provide here an example of a method which can make it easier. If you do a lot of routine map requests, you might actually want to have a method or something which does it for you, because there will be a lot of parameters you will repeat. For example, you will always use the same format type. You might want to have the same projection, and these kind of information you want to actually always the same for your map. So you can put them in a method, and then you can reduce your calls for the get map to what we call here the get map method, and then you have a simpler code for that. But what we do here is we actually, as you saw in the example I done earlier, if you request one layer, you just get the layer. There's no information with it where the location actually is. So as a support for that, we offer various layers, like we're using here the background, which is actually you can see it's the landmass shaded in this nice, how you call the color? Tan or beige, yeah. Skin color. Yes, beige skin color. So that's the default background. And then the foreground is actually the coastlines to go with it. So these are the 2 layers which we put here just for the orientation. What this code allows you, you can change it, and you can take, NASA has a nice web map service on, what's it data called? This Blue Marble, yes. So you could actually take that as a background instead of this fantastic beige one if you want something more interesting or something more vibrant. So this is your option now with the WMS, that you have every layer separate. You can actually take them from different services. So, sorry. So what I would suggest is, if you want perhaps to spend 5-10 minutes on this example, might want to change the layers, please also feel free to change the location. I mean, here this is now global. You might want to try Europe or something like that. Try to play around a little bit with the WMS.
Is there any directory of like services that use this standard? And also, are there any? You've got a very global one here. Are the ones that do? So, if you want to look at UK, break the UK down by postcode, or other things available?
There's quite a lot of services. Unfortunately, not a real registry. There are some pages where there were different people were trying to build these kind of, but they're sometimes out of date now. And you will find that there's a lot of servers which have come and go or have been renamed. There's quite a lot in the US. There is, as I said, there is actually every member of the European Union has now to have for Inspire these national services where they have geodata. The Inspire portal of the UK should have some layers.
Inspire?
Yeah, Inspire UK. Okay. So there you should, or is it data.gov?
Data.gov.uk.
Yes. Yeah, data.gov.uk, I think that's the link to that, yeah. So there you should find a lot of services actually, but there's also a lot of web map services. But as I said, there will be different location. Then there's definitely you want to check the boundary blocks, what area they're covering. Anybody else a question?
I see you're specifying size here.
Yeah.
So that must do a resample of the data before it sends you the map.
Yes.
How do you know at what point you start subsampling what's available?
It's very hard to judge from a client side when you do that. I agree. That's not how I can say the ideal thing of the pipe. What you can actually do is if you leave it away, you should get the highest. So or let's say this way, you expect that the service provider, when they set up the service, they specify what would be the default, and ideally it should be the best resolution. So you normally only give it if you want to have it smaller. So that's ideally. Does not mean that everybody does it like that, of course. But the standard allows you to set a default, and normally it's suggested to use the most quality one. So ideally, if you leave it away, you should get more. But then you have to be careful with aspect ratio and things like that. So it does not come out of the box. You might have to play with that. But there's a bit of trial and error, unfortunately. But everybody is able to follow and to.
I didn't understand what you meant by the blue marble
Hmm.
thing. Is that just one of the styles that you can?
No. Blue Marble is actually a web map service from NASA, or it's actually the NASA did took satellite images of the Earth and built a mosaic of the Earth with clouds removed and things. It's a very, very nice, sleek view of the Earth. And they provide this as when you go search Blue Marble in NASA, you will find they have a web page where you can get these high resolution JPEGs in TIFF, but they also have a web map service where they serve it out.
And does that use can I use the same Python library to?
Exactly. That's a nice thing with the standard. All WMS you should be able to access through the
OS lib.
the
URL when you create the
Exactly, the URL we gave in the beginning, yeah. Let me go back.
So do all these government data sets, they all stick to that standard, do they? They all have that standard?
Depends what they're serving, because you will find there might be from the UK. I think there's some about street information for roads and streets,
Yes.
and that will be vector data. So they use the web feature service.
Okay.
So it does not have to be all coverage, or the web map service. So they have different services. Yeah. But they're trying as much as I know to follow the OGC standards.
Yes.
Yeah.
Yeah. Sorry?
What's the format for the bounding box? Maybe I'm doing something wrong with the plots, but this is not the latitude 55, it's around 50.
Yeah. But did you...
Just put a global bounding box in here and use it everywhere.
The global... Oh, here. Okay, hang on. I'm not quite sure. Like, it's... Okay, hang on. If you go up, then we could specify. Then we can see. Okay, basically here. So we see it's latitude, latitude minimum, longitude minimum, latitude
okay,
maximum.
I got it the wrong way
Yeah.
around.
Yes.
It's not long. Okay,
Yeah.
thanks.
Have someone with longer arms.
So would you like to have a bit more time, or shall we continue? Because we would now switch from the web mapping service to the web coverage service. Maybe, yeah? Okay. Okay, good. So now we actually interested, because we have large volumes of data, to get the real data values and also to process the data to get actually information we're interested in, and not predefined maps and layers. So and there's also from this Auslib library, the standard one is supports also a web coverage service, but just a web coverage service version 1.0, which doesn't support the processing functionality. And then our server is also already the version 2.0. So that's why we, a colleague of ours, he modified the Auslib library, and basically you can fetch it from this GitHub account here to that the Auslib library also supports a web coverage service with the version 2.0.
And these changes, we should say, they're in the process to go in the mainstream Auslib.
Yeah. So we're in the process that it actually supports also 2.0 soon. But on the Jupyter Hub, basically, we already installed this version of the Auslib, so it actually should work. So we start off actually with the same way as we start with the web mapping service. We build a object with our web coverage service, which is here the URL to our service. And then we can specify, then we can see actually to see what data is actually available on the service, where we go from our object, from our web coverage service object, we go to contents, and then the keys. We want to actually get the coverage names. And if we let it run, you should also get all the different coverages available from the service. So soil moisture, temperature on 2 meters, temperature on pressure levels, river discharge forecast data, etc. If we want to get a list of available properties coverage has, we can use this with the key contents, and then specify on what coverage we actually interested in. So in this case, 2 meter air temperature, but we can also specify sea surface temperature, for example, or particulate matter 25. So we go through, and then we can see we can get information on axis descriptions, bounding box, the grid definitions, different supported formats, etc. So now we know what data is available, but still, if we're specifically interested in one data set, we want to know like what specifications does this data set have? Like, so what bounding box from what temporal context we can use the data, etc. So, for example, with the key contents and then our data we're interested in, and then bounding boxes, we can see what bounding box the data refers to. And here we have to apologize, or at the moment we have some difficulties because we come from the metrological domain, and the GIS domain usually works with pixels, and the metrological domain works with data points. And so there are differences how to specify a grid on our data. And because I come from a GIS background, if I see data with minus 90.25, I wouldn't trust the data. But it's just at the moment, because one idea of this project is to see how we can actually map the metrological data on a web coverage service. And so we're working on it to make it right. And we can say the data at the moment, they are right. And actually, it's going from minus 90 to 90 and minus 180 to 179.75. Okay, And then and we can also get some more information about the entire grid our data contains. So if we use, instead of bounding boxes, we use the grid parameter or the grid key, then we get the grid information. And then after a while, it tells us that our data is a three-dimensional data set with latitude, longitude, and ANSI in this case is the time axis. So we have 3 dimensions. We have the number of pixels or data points available, and also the resolution for every axis. So in this case, we have some 0.5 times 0.5 latitude-longitude grid, and here a 0.25 per day. So basically, every 6 hours is the temperature available. And then we see the origins. So here the latitude, it starts at 90, the longitude at minus 180. And the time information starts at, so here we also have the offset again. It starts actually on 1st of January 1979. So this is, we now have more information about the data we're interested in. And then, because now actually with large volumes of data, we're not specifically interested in JPEGs or PNG, so not in image formats. We're actually interested in data formats we can actually work with. So either to get the raw data via CSV or a NetCDF file. Are you familiar with NetCDF format? No, okay. So basically, a NetCDF format is quite often used in climate sciences. So it's very, how do you say? There's a good library also from Python, and basically it can store multi-dimensional data within one data file, and also all the metadata that belongs to this to the parameters basically. And so, yeah, so climate scientists or also GIS people or with a GIS background, they often use NetCDF data files. So basically, we can see in what formats the data we can actually retrieve from a web coverage service. And so there are different options. So we can retrieve the data in a CSV or as a JSON, which is actually very useful if I want to do web applications, for example, and then also normal image formats such as PNG, JPEG, and TIFF, but this is not what we're interested in on a web coverage service specifically. So if we want to use the Auslib library to actually get the data, we can use the get coverage request on our WS object. And then we can specify like what data we're interested in, also what subsets, so if we want to have the global image or a geographical subset, and also the format we're interested in. So in this case, we're interested in a NetCDF for a global coverage for the 1st of August 2003. And then it is basically downloaded, and then we can load it with the NetCDF4 library, and we can directly plot it. So basically, we request here the file. The file is downloaded and stored, and then we open the NetCDF file. And we construct a dataset object from the NetCDF library, and this dataset object we can then plot with Matplotlib, for example. So if we let it run. I just want to mention it could come to some problems with if we run it everyone, because we are limited space in the Jupyter Hub, and so we have 7 gigabytes and so I think 60 people can run it, and then we will see. But it's also good to test our services and systems. So basically, this is without any. So without a lot of data download, basically, we could get the information we needed, and just with some lines of code, we could load our data. Any questions so far? No. Yeah.
Is it possible to produce an animation quite easily?
Sorry?
Is it possible to produce an animation, a GIF?
So you can produce animations, yes. So basically you can, from a netcdf file, you can also get, because now we downloaded a 2-dimensional file, but you can also store a 3-dimensional file, and then you can go through the time information, for example, and then you can produce, yeah, videos or GIF or animations, yes. Okay, so then I would continue to another. So this was actually how we could benefit from the Auslib library, but still this was shown that we still have to download the data and then load the data again. And with our volumes of data, for example, 1 parameter of 2-meter air temperature from 1979 to 2014, we have like 27 gigabytes. So we actually don't want to download a lot of data, duplicate data, and so we actually want to get the data or access the data, process them on the server side, and just get the information we're really interested in. And so another way to actually work with a web coverage service and a web coverage processing service is to request the data with a HTTP request, and then store the data directly in a NumPy array, for example, or in a Python list. And so in this example, we aim to retrieve a time series of global monthly averages of 2-meter air temperature and store it as in a Python list. And here, as as I explained before, we take advantage of the process coverage request. So basically, we already process data while we access it. And so the access point is, again, our web coverage service. The request type is process coverages. And then we specify a WCPS query. In this case, it's still very simple and understandable. So basically, we want to have for every point in the 2-meter air temperature, please give us back from 2001, 1st of January 2001 to 31st of January 2001, the 2-meter air temperature in degrees Celsius, not in Kelvin. And we want to have for this, for the global data, an average. So we want just to have one value, the average 2-meter air temperature for every day for January. So in this case, we specify the URL which we can access our data, and we specify it as a generic URL. So basically, we can also apply it for other coverages. Or other parameters we're interested in, and also other time information we're interested in. So this is our form or request we can use generically. And then because we, yes, so we need some, because we interested in just retrieving the data from January and February and March and April. We have to have a helper lists for handling these datetime objects. So this is just two for loops which help us to specify the start date and the end date of every month. So 30th of January, 28th of February, etc. So basically, we just, and if we look here, so the start date list gives us then a, should give us something. Ah, yes. So it gives us now like a list for the year 1979, and the same for the end date list for every last day. Okay, and with this information, we can now loop through the generic URL request we set up before, and we build up our URL or our request. We're interested in 2 meter air temperature, and then we just get the information from the start date list and the end date list. And in the end, we want to have a Python list of the global average for every month for 1979. So this might take a bit, but should actually work. So now the entire data is actually accessed and processed at the same time. And then we will see.
So this whole processing is happening on your side?
Yes, on our on server side, yes.
So we are simply sending you a request saying, okay, I'm interested in a particular parameter on a particular region in these bounds of lat long or anything as such, and you process it and you provide that information back.
Yeah, yeah. So
if I'm asking for a whole globe as such on each and every parameter, how much time does it get request timeout? What's happening?
Yeah, so this is also part of the project we investigate. So is it scalable? And of course, with these kind of services, it's very easy to access terabytes of data. So people wouldn't recognize that they actually ask for terabytes of data. And so this service we have to limit it somehow. But at the moment, it will not go beyond, but we didn't set a specific limit. Yeah. Yeah, okay. Any other questions? Okay. Okay, so now it should have been processed, and we have now a list of monthly averages time series for 1979. And the same we could easily do for another year, or not the global information, but just a geographical subset, for example. Okay, any questions so far? Okay. Okay, this was like just how we can store time series information into a Python list. But geospatial information, we often have multi-dimensional fields. So actually we interested in also to store directly, to access multi-dimensional data and store them in the NumPy array, and then we can work with them further. And so this is a more advanced example here. So basically, so our 2 meter air temperature is a 3-dimensional data set from like a global data set from 1979 to 2014. And we want to have for every month, we want to have the average basically but for every data point. So we instead of, because before we just averaged over 2-dimensional field, we want to average now through time, basically, through every month. And so this is also possible with this web coverage processing service. But as we see here in the query, it gets a bit more complex. So basically, we also process the data. So we convert the data from Kelvin to degrees Celsius, but we take like the latitude, the longitude, and the time information, and we condense the data over time. And here we see, if we specify a plus here, we say, okay, please sum it up, and then later on we divide it through the number of files or through the number of information we have. So we know that this is like another language people have to use, and this is also, we also admit that it is not very straightforward to understand. But at the same time, like if you have examples like this, it also gives you easily a processing functionality on top of our data and multidimensional data sets. Okay, and so in the end, it's a similar setup here, just with the or as before, just with the difference that we have now a empty NumPy array, which contains like the global data field, and then for every month, like we have 12 global data sets in the end, because we have the average for every month, basically for 1979. And this might take now a bit longer to, oh, okay, I haven't specified this one. Okay, this might take now a bit longer because basically we get the entire 1979 data information and process the data through time, so through the time information. But in the end, we have a raster stack, we call it, of average 2-meter air temperature information for every month. And if we specify here with the index 8, then we get the for the month September, for example. Okay, so there were like any questions? I think it's quite, it's also a lot. So we gave now two different opportunities how to access the data. So either with the Auslib library to play around with a web coverage service, or also directly request the data with a HTTP request. I don't know how we do it in time. We set up two different examples how a web coverage service and requesting data via HTTP request could be very beneficial for some use cases or to create a geographical workflow. We can do it either to that we have one example that we guide you through, and then another example you can do it yourself, or we can also guide you through both examples as you wish.
I think
no.
I would time myself.
Okay. So basically, one example where we can benefit from the processing functionality, and also where we require actually a lot of raw data for little information in the end, is a climate graph for any location on the world, basically. Because the climate graph contains the long-term average, minimum and maximum of the temperature, and also long-term average precipitation for one specific location, and for each month. So basically on the raw data, we need a long time series of information, and best would be to have like global information, because then we can easily pick any geographical latitude and longitude. So this is actually what we aim for. This is like a matplotlib plot. We can also do it prettier. We also see that London is quite wet. Okay, basically what data is required, and also what data we offer at ECMWF is reanalysis data, what Stefan said before. We have 2-meter air temperature and also the total precipitation running from 1st of January 1979 until almost near real time, like until now April 2016. Our data is in GRIP, which is a binary format, and even less used than NetCDF. And so basically, if people are interested in our data, we don't want to have them using GRIP, because it takes quite a long time to use the data. That's why we're interested in building up these services, because then you don't have to think about any specific format anymore. You just get the data values, and you can easily store it in a NumPy array and then do your processing or your workflow. So basically our data is global data, 6 hourly data from 1979 to 2016 or 14, and the entire data volume is 27 gigabyte per parameter. So the workflow to create a plot for a climate graph would include to retrieve first the monthly mean, min and maximum 2-meter air temperature from January 1979 to December 2014. Then to retrieve the monthly sums of total precipitation. So for precipitation, we're interested in precipitation sums and not in the average, basically. And then to calculate the average for every month for every parameter. And then once we have this information, we can easily plot it. So we load some libraries which are required to like NumPy requests to request our HTTP requests and also matplotlib, for example. And because we work with datetime, we also use the datetime library. So we specify our WCPS queries, and this is the query we also used before. So basically, we take advantage of a mathematical condenser function, so either average, a minimum, or a maximum. And so before we specify here our subset of the data, we can here specify a generic placeholder where we can then later can specify if we're interested in a minimum, the maximum, or the average of the data. And so we have two different formats for the temperature and the precipitation, because temperature we want to convert from Kelvin to degrees Celsius, and precipitation we want to convert from meters of water to millimeters of water. So okay, and here we have the same helper functions to go through the entire list to specify our first day of the month and the last day of the month. And I just say that I don't let it run because it would take a longer time. We try to run it, and through this Jupyter Hub, it might take, like on your local machine, to retrieve the data around 10 minutes because we request 27 gigabytes. But here for the Jupyter Hub, it took a bit longer this morning. So basically, but it's the same here. We just make a cast. If we talk about precipitation, we don't start on 1st of January 1979, but on 2nd of January 1979, because it's forecast data. So the data has to be processed specifically, and so we only have the processed data is only available or starts from the 2nd of January. And then we go through the start and date end list. We request the data. In our case, we can specify the latitude minimum and maximum, and the longitude minimum and maximum, and also the date information we get from the start date list and end date list. And we all store it in a Python list, basically. And so this is our function we build up. So the function is called retrieve from WCS, and we can add to this function the parameter we're interested in, the operation we want to conduct. So in our case, what we set, what condenser function we want to apply. So minimum, maximum, or average, and also the latitude minimum, maximum, and longitude minimum, maximum. So for London, we specified the latitude and longitude information, and then we can actually retrieve 3 different lists for a monthly time series for 2-meter air temperature, and then we're interested in the average, in the maximum, and in the minimum. And then the latitude and longitude information is then taken from above. And the same we do for the precipitation, but just with the difference that we want to add, so we're interested in the precipitation sums rather than an average. And so we would generate these lists, and then basically, once we have these lists, we have a function where we then we get through the entire time series, and we retrieve every information for January, every information for February, and then we generate the average for every month, basically. And then we end up with 4 different lists of with 12 values of the averages for every month. Okay, and then we can, once we have this information, we can basically plot it. So this is an example with matplotlib, but there are much nicer ways to plot it. This is just an example. And the plot we already seen above. So we use the pandas data frame to bring all the data together and then to easily plot it with matplotlib. So this was one example of a workflow where people can easily access the data, process the data on the server side, and no data download is basically required to create a climate graph for any location. Any questions so far? Yes?
So here you requested just one single point. Do you still need to load all the 27 gigabytes in your backend?
No, it's just one single information. Yes.
Why does it take 10 minutes?
Sorry, I misinterpreted it with the other example. So this might be no. It should be faster. But in general, we also have to see that with geospatial data, it depends on the data model, how you structure the data in the database, depending on how users want to actually access the data. And you have to find a compromise between geographical subsetting and also time information or time series retrieval. Yes.
Just one question.
Yeah.
Why grip of overnet CDF?
Sorry?
Why grip overnet CDF?
So why we offer the data in group and net CDF?
Yeah. So you said that meteorological data or meteorological data modeling, most of the time it is doing in net CDF.
Yeah.
GRIB is less likely used format. Still, why it is been? Is it?
No, the GRIB is the international standard to exchange numeric weather forecast data. It's a UN body who decides and to ensures for decades now because weather services around the world work very closely together, and it only works if you have very clear standards to exchange. These are not common standards. It's actually very much used. Whatever forecast you ever get will have been based on data in GRIB format, but you will never see it. It's a very closed system which relies on this one. And when I say we have 180 petabytes data, most of that is in GRIB format. So if you talk about the amount of data, it's perhaps more used than many other formats you think are more widely used. There's a massive amount of data in this format, but it's not widely used. It's not common. Not many tools can handle it. It's not very common outside our specific community. It's very specific for meteorology. NetCDF is more wider spread. There's more tools. It's more available. Tools available. So it's used, but it's not public. It's not if you give it out that many people can do something with it. That's why it's a service.
I have a question, and I'm a little bit afraid it is too broad. And it is, what was the workflow before you introduced this? And what sort of changes and feedback you are getting along the change?
Yeah, no, it's a really good question, basically. So, yeah, the usual the former geospatial workflow, how also it is taught at university, is you go to a site, for example, to NASA or to ESA or to ECMWF, you download all the data you need, then you use either a geographic information system, or if you're already more advanced, then you use Python or R to process your data, which worked well 10 years ago when we also didn't have open data yet, and also we didn't have like these very good data sets with a high resolution. Now we already, Stefan introduced the Copernicus program, so it's a new fleet of satellites, of 6 different satellite fleets, and they produce like very high resolution images, and they expect to have 2 terabytes per day from the satellites, basically. So most probably users, they come to their limits to process the data on their local machine, to process the data and also to store the data somewhere. And also from our perspective as a data provider, it's not our interest that there are like multiple copies of our data. So our data archive is at the moment around 180 petabytes, and there's no way to copy this data. So it's also of interest to us that not everyone is actually downloading massive amounts of data and just getting the data the user actually needs. So it's basically just not a requirement to download data anymore, and also to apply, even if it's just simple processing functionalities, because with more advanced data science, you can't apply on a web coverage service, but it already helps you if you can retrieve a maximum or minimum from server side from a large data volume, rather than downloading it and then loading it into your Python script and calculate it from there. Yeah. Does it respond to your question?
Sort of. I thought the previous workflow was based already on data services. I mean, XML is a very good thing for machines. Just I was wondering about like if you had any story that I can then sell in other places to convince people to use Jupyter Notebooks about how it gets easier to have some sort of a front face to XML services.
Okay, so XML, I would say it's always machine to machine. So it's very powerful. So machine likes it, people, I don't know if they like it. So to go in this Auslab library, it basically just goes through this XML and helps you to retrieve the information you need, rather than yourself building up the script to go through the XML document. And Jupyter Notebooks, like before, as every workflow, like you had the data somewhere stored, you had your script somewhere stored, and then you had your visualization also somewhere. So basically you had like, and the documentation, sometimes it was missing and sometimes it was there. But you had like on different places the information. And like Jupyter Notebooks, you have everything in one basically. Yes. Yeah. Yeah?
So OWS lib is only for client program. I cannot use it for example, local data or my own server on my local computer. I'm depending on answer on remote server.
Yeah, so it depends on the standardized OGC web services. Yeah. Yeah. So if you have a standardized web service and it follows these standards, then you can also access it. Yeah.
Can we get some weather forecast data from this service, like what will happen tomorrow?
So the forecast data, they're not openly available. So they just available for our member states, and so far we have like near real-time data available, but not a real forecast data.
So what does that mean? It's like
near real-time is about, like, for example, like reanalysis data. It's about last month. So we have now May, like mid of April now is available. Yeah.
I think there's some forecast data like the atmospheric services, the air quality data. This is actually available as soon as possible. So that is. So when you talk forecasts, there's different forecasts. When you mean the weather forecast like precipitation, wind, that you get through the national agencies. But you will be surprised how many national agencies have web APIs. Not all OGC, but some have their own web APIs where you can get time series information for location, like the Met Office. I think it's open data. They have different services, national weather services, so you can get information from them. And they have more high resolution, and they have a lot of services also for the 1 and 2 day forecast, which you might be also very interested in. But that's why it's worth exploring your national weather service, what they offer. There's a lot of projects and ideas now to open up data. Yeah.
Okay, I think we're almost towards the end. That's why I suggest, so we prepared another example of a geospatial data workflow which climate scientists often interested in. I don't go through this example specifically because it's a bit more complex. But we try to document it as much as possible. And basically in this example, we interested in retrieve these information. Like this graph, probably a lot of people already seen that we have global warming, and yeah, our globe is getting warmer. And also, like, this is general information from the entire globe. And then we can also get for specific months this information. And basically, you can also create these kind of graphs based on our data and with the help of these web coverage services, and you don't have to download the data. But I suggest you, so we build it up again in this way. What is the objective, what data is required, and also the different steps of the workflow. And then you can have a look through it, and we will still be available here, and you can also ask any questions. So we said at the beginning, this is something very new for us. So it was kind of our first tutorial. We also have a feedback form, so please give us feedback anyhow, like positive or negative, especially negative, because then we can improve. So yeah, it doesn't take 2 minutes, it would be, and we would really appreciate it. Okay, and yeah, I hope you liked it, and
I think in 1.5 hours we can only start giving you ideas. It's not, you're not now certified geospatial professionals, but yes. I think we try to give you different aspects of it, and I hope at least some parts of it are interested for you and help you.
Okay, thank you.